Hi, this presentation will be an introduction to texture mapping. The texture map is a pre-computed image, usually read from a file, that can be then sort of painted onto a surface as you render it. Lets you render detailed images even without using super small triangles. You can find everything I'm talking about in chapter 6 in the book. This is from the first part. So a texture map, or just a texture for short, is an image or another set of data, usually a two-dimensional array, that can be used when rendering, usually read from a file, but can also be pre-computed. And as a picture example of this, we might have an image, like a JPEG file, with a picture in it, say, of a Christmas tree. So here's a very stylized picture, Christmas tree. I'm not much of an artist. And we are rendering on the screen some pixel. And the pixel will be given texture coordinates, which is a pair of scalar values. Usually we use letters S and T for texture coordinates instead of X and Y. And the idea being that S0 and T0, that the texture coordinates index into the image. So the convention is that S0 is at the left side, S equals 1 is at the right side, T equals 0 is at the bottom, T equals 1 is at the top. So we're indexing by the ST coordinates, as it were, but with S and T ranging between 0 and 1 into the image. And if S0 is the value here, and T0 is the value here, and then these are the coordinates of a pixel. And when we render the pixel on the screen, it uses the texture coordinates, S0 and T0, looks up the corresponding position in the texture map, and then uses that data either as a color or as a material property or some other property to help render the color of that pixel. So there's a lot of advantages to this. One is, already mentioned, is you can render small detail. Makes it possible to render small detail much smaller than the size of a triangle. And more generally, a texture map can serve as a lookup table. A texture map can serve as a lookup table for a two-dimensional array for any kind of data. So just to expand a little bit on the first advantage, how would we render small details even though we have big triangles? Think of this texture on map being rendered on top of triangles. So we might render some triangle on the screen like this. And the triangle, it's first specified as a triangle in 3 space. It's then mapped by the model view and projection matrices into the screen. And then here we've got 3 corners, x1, x2, x3. And these 3 corners have as vertex attributes, maybe they've got texture coordinates, S1, T1, S2, T2, and S3, T3. So these things are vertex attributes. They might be specified in the BBO along with, say, the vertex position or the vertex normal. So each vertex has vertex attributes, and then we would compute S0, T0 as a weighted average of these 3 things. So this would be equal to some alpha times S1 T1 plus beta times S2 T2 plus gamma times S3 T3. And in this way, although the triangle is much bigger than the details on this picture, the pre-image of this triangle would correspond to some points over here in the texture map. And we would pick up the colors from the pixels inside the texture map and put them onto the pixels on the screen, thus able to render small details from the image into the screen, even though we've drawn a big triangle. Now I'd like to do an example of how to assign texture coordinates for cylinder. So, strictly speaking, I'm going to be assigning texture coordinates to the sides of a cylinder. So for the cylinder, I'm going to use the canonical cylinder centered around the y-axis of radius 1 and height 2, centered at the origin. So here's the x-axis, the y-axis, the z-axis coming out of the board, and the cylinder itself will go from, here's the top of the cylinder will be at y equals 1, the bottom of the cylinder will be at y equals minus 1, and it has radius 1. And so a point on the cylinder is going to be specified by the height and the angle theta. I'm going to use c of theta y as a parametric equation for the cylinder. And I'll use c of theta y equals sine theta, that's the x value, y cosine theta, that's the z value. And what we're doing here is we're going, think of angle theta with the zy plane, and we're rotating around this way. And I'll let, for this case, with minus 1 less than or equal to y less than or equal to 1, and theta will be in the interval minus pi to pi. So minus pi less than or equal to theta less than or equal to pi. So here I've done the coordinates of the points on the cylinder, and now I'd like to talk about the texture coordinates. So the texture coordinates, what I'm going to use is I'm going to use, again, I want to think of unwrapping cutting the cylinder open in the back and flattening it out into a rectangular image. The texture coordinates will be functions of y and theta, and I'll use s, which is going from left to right, will be theta plus pi over 2, and t will be y plus 1 over 2. In particular, this means that 0 is less than or equal to s is less than or equal to 1, and I'm sorry, I meant 2 pi here. S is theta plus pi over 2 pi, and t is y plus 1 over 2, so t is also between 0 and 1, just because theta ranges from minus pi to pi, and t ranges from, y ranges from minus 1 to 1. And if you look at this, what this means is a point, if we unwrap the cylinder, let's do a top view here of the cylinder. So with a top view, I've got z pointing downwards, x pointing rightwards, and here's the top of the cylinder, here's the center, and so theta equals 0 is in the front, and that's where s equals 1/2, and theta equals minus pi is in the back there, but also theta equals plus pi is in the same spot there. The theta is wrapped around. So although we could either use minus pi or plus pi for the very back of the cylinder, we then use values of theta between minus pi and pi for wrapping around the cylinder. Whereas the t value, t equals 0 at the bottom, t equals 1 at the top. And this lets us assign texture coordinates to the cylinder. So for instance, we might have a map. So here's some texture map, which with some image on it. So, you know, maybe the image says tomato soup. You know, the famous Warhol paintings of tomato soup cans. Think of an image like that that's then pasted onto the cylinder just like a label on a soup can. And again, s equals 1/2 would be in the middle here. S equals 0 would be on the left side. S equals 1 is on the right. T equals 0 is in the bottom. T equals 1 is at the top. And we're wrapping it on in the natural way onto the cylinder, onto the sides of the cylinder. So a sort of strange thing happens on the back of the cylinder. Suppose we do a back view of the cylinder. So in the back view, I guess the x-axis is pointing this way, the y-axis is pointing up, the z-axis is pointing away from us, and right here here's the back side of the cylinder. And right here down the middle of the back is the s equals 1 on this side and s equals 0 on this side of the seam, where theta equals pi on one side and theta equals minus pi on the other side. So strange things will happen if you have triangles crossing this seam. Suppose we're trying to render, say, a pair of triangles that go across the seam in the cylinder. So here we would have s equals 1 minus epsilon, and here we would have s equals epsilon. Suppose we've gone angle epsilon away from the back on both sides. Well, where do these points correspond to in the texture map? So these things correspond essentially to here. Here is s equals 1 minus epsilon. And here is s equals epsilon. Okay, now what's going on here is when we render this, what we really want to do is we want to pick up the two sides of the texture map from s going from 1 minus epsilon up to s equals 1, and then wrapping around s equals 0 and going up to s equals epsilon. Now, if we're not careful, and we just did this in the default rendering, that wouldn't happen though. Instead, we would get this other triangle going across this way, wrapping from s equals 1 minus epsilon backwards to s equals epsilon. And you would see the whole word tomato there flipped around in a very narrow region, sitting here on the back of the cylinder when you render the texture map. So we don't want to do that. So the fix for this is I'll switch back to black here. So the fix, by letting s equal 1 plus epsilon. So where's s equals 1 plus epsilon? Well, it's here, right? And so what we're doing is we do what's known as wrapping. We wrap the texture map. So here's another copy of the texture map. And now, when we render with s equals 1 minus epsilon and s equals 1 plus epsilon, we get this region, the right-hand side of the first tomato soup image for s between 0 and 1, and then the left-hand side of the second tomato soup image between s equals 1 and s equals 2. So s equals 2 here. So this wrapping, here this is known as wrapping the texture map image. Another word for this not really used would be tiling. Tiling the whole plane with a texture map image. Wrapping refers to wrapping around from the right-hand side of the texture map back to the left-hand side texture map. This is actually known as wrapping in the S direction. You can separately wrap in the S direction, but also can wrap in the T direction, so that if you take T values bigger than 1, you get another copy of the texture map up there. So by texture mapping, by wrapping or tiling, we can take care of problems like this. For another example, let's consider a surface of rotation. This is something you'll be coding yourself in Project 6, at least if you're in Math 155A in fall of 2020. So example is texture coordinates for a surface of rotation. So here the picture is we've got some surface of rotation. Maybe it's sort of the sine r over r function like we did in the programming assignment, or some other shape. Actually, that doesn't particularly matter for the way I'm going to assign texture coordinates. I'm going to assign texture coordinates by looking at the top view only. And in the top view, looking straight down the y-axis, this thing looks just like a circle. So here's the x-axis, here's the z-axis, and we'll have points here. For instance, here's a point at radius r and angle theta, and of course it's got coordinates. Let's do a different theta. I drew it where I don't like to usually do it. Let's try this. Radius r and angle theta. So this has coordinates. Z is r cosine of theta, and x is r sine of theta. And we'll just do rectangular placement of texture coordinates on top of this. For our texture coordinates, we'll think of this as being a radius 1 circle, but you can obviously adjust the radius however you want to. We'll just take the texture map and place it on top of this. So here's the texture map. So this is s equals 0 on the left-hand side, s equals 1 on the right-hand side, t equals 0 on the bottom, t equals 1 at the top. And the texture coordinates for this point, this is going to have some texture coordinates st, where s, and t, we think of s as going from here to here, so s is going to be based on x value, but we want to, instead of having x go between -1 and 1, here's x equals -1, here's x equals +1, we'll let s be x plus 1 over 2, and likewise t can be minus z plus 1 over 2. And this will pick out the circular section of the texture map and draw it on the surface rotation, imposing it straight down from above. The corners of the texture map won't get used in this, so they'll just be discarded. So you'll want to take account of that when you're designing a texture map for this kind of thing. So this is the kind of thing you'll do in Project 6 if you're in fall quarter of 2020. The only adjustment that needs to be done, really, to what I just said, is that the radius of the circle of rotation is not 1 in your programming assignment, it's a different value. So you'll need to scale the values that are used for the computation of S and T appropriately. As a final example, I want to use texture coordinates for a sphere. So here we're going to be thinking of assigning a single rectangular texture map onto the surface of a sphere. A surface of a sphere being round, you have to have some points where you don't get smooth assignment of points. But here's a sphere, and we'll say it's radius 1. And we'll say centered at the origin. And we'll use the so-called cylindrical coordinates. It's also possible to use spherical coordinates, but I'll let you look that up in the textbook if you wish, and I will just discuss cylindrical coordinates. So for cylindrical coordinates, let's draw the axes. Here's X, here's Y, here's Z, and we're going to do the following. Y is ranging, so Y is ranging from -1 at the bottom to 1 at the top. So our texture coordinates we'll start off, the easy one is T will be Y plus 1 over 2. Since Y ranges from -1 to 1, T will range from 0 to 1. And then other points on the sphere are going to make some angle, theta, with the YZ plane, I should say. And so those points will get the texture coordinates just as before. We'll use S equals theta plus pi over 2 pi, where here now theta is ranging between -pi and pi, so thus S is ranging between 0 and 1. So this is the spherical coordinates. Another way to think about this is you're putting a sphere around the sphere, putting a cylinder around the sphere, giving the cylinder the same type of texture coordinates we used two boards ago, and just projecting them horizontally in and placing them onto the sphere. You'll notice there's some bunching at the poles. The top of the texture map, you have a texture map here. S goes from 0 to 1, and T goes from 0 to 1. The whole top of this thing gets mapped to the North Pole. The whole bottom of this thing gets mapped to the South Pole. So if you looked at the image, the image is going to get scrunched up at the poles as it gets wrapped around the poles. This is a common dilemma for map makers. There's no really excellent way to draw a spherical shape onto a flat surface without some sort of distortion. Likewise, in our application, we're going from a flat surface to the sphere, and if you do this with just a single map like this, there's always going to be some kind of distortion. We will see another way to map texture coordinates to spheres when we get to environment maps, but that'll involve multiple images and a different type of distortion. That's the end of this presentation. Thank you very much.